like I assume you're not in an experimental condensed matter group, so that's fine.
Okay, it's being live streamed now.
What if I know about them there? I absolutely.
No.
I'm hungry.
Yes.
What's
it's a derivative of energy or something.
Oh, that's
Yes.
What's Q? What's the not? What's the Q? What's the Q? Is that a unit of is that a unit of
Yeah.
What's Q? There's like what again?
You know what? I can't say that on camera.
So, yeah, so Aryan, we're gonna use that like the same constraints in time as the actual representation. So yeah, 15 minutes to do your thing. The rest of the time is open up to questions. And yeah, take it on.
All right, dear committee members, thank you for being here. And I hope you enjoyed this completely winged presentation on my research this semester, which has really kind of been in two phases. One part, it's for temperature control of experiments, and the other part is actual studying the energy spectra of copper-silver alloys. So the outline, basically in the first half, we're going to talk about my work on a temperature controller, kind of the theory behind it, how the setup works, as well as the specific characterization I did of it, and where it's going to go at some point in the future. And then we're also going to talk about some X-ray emission spectroscopy I ran with copper-silver alloys, talk a bit about the theory of that, what I obtained, and what we do next with it. So without further ado, let's begin talking about temperature control. So basically, we're an experimental condensed matter group, and so we want to run experiments with different samples. And it is really cool for us if we can compare or we can control the temperature of our samples, because that can allow us to elicit different properties and, potentially like send them through phase transitions and whatnot. And in particular, the kind of, we'd want to control things that we then run X-ray spectroscopy on, which I'll discuss in the second part. So basically, we need to heat and cool things. Now, heating is kind of easy. You get a resistor, you run a bunch of current through it, and that heats according to Joule heating. So that part is simple. Now, cooling is somewhat less so. I mean, there's lots of options, fans, water cooling, whatnot. We want to use solid state cooling because there's no moving parts, so there's no vibration, nothing complicated to interfere with our experiments. It's like nice and compact. And so you can do solid state cooling with a Peltier cooler, which uses the Peltier effect. Basically, a potential difference, a voltage difference across two terminals creates essentially a refrigeration cycle. So you can see here, we've got a negative terminal, a positive terminal, and what is essentially like a p-n junction. These are semiconductors. And so the negative, so let's say this is the side we want to cool. The negative charges will flow upwards towards the side where the heat will be released, and they'll carry heat with them. So that flow of electricity allows us to create a temperature gradient. And in an actual Peltier cooler, as you can see down here, we would have a whole array of PNs in series that together are providing heating and cooling through the movement of charge carriers and electrons. And so the cooling we can achieve here is given by this. So it's proportional to this thing called the Peltier coefficient, which is just a kind of a system characteristic. Now, it's an electronic system, so it also produces waste heat. And so that means there is eventually steady state. It cannot get arbitrarily cold because eventually the heat removed is matched by the heat created by the electronics. And these are very inefficient, but like I said, the lack of moving parts makes it great for the kind of condensed matter applications we're looking at. So I came in this January with sort of a half-built existing setup. This is the Peltier cooler, where this top side is where we would mount a sample. Like we have a little ring on here, and it would get cold via contact with this plate. And then, inside is like all the semiconductors and stuff. And then on this side here, so this is the warm side. And then this is a big heat sink over which we blow a fan to try to prevent it from getting too hot. And so this is like the hot side. There's a bunch of electronics to power it and whatnot. And yeah, and so this, it's just powered by some standard power supply, and it receives a direct current, and it just has a constant cooling capacity. And so you start it out at room temperature and let it set for a bit, and it'll eventually reach a constant temperature. Now, the important thing to know is that The if for a given Peltier cooler, the temperature gradient it can maintain, it can only maintain so large of a temperature gradient between hot and cold sides. And so if we want to get the cold side colder, we should make the hot side colder as well. And so that's the point of the fan, and I'll discuss a little bit more about that as we go. So yeah, so here's a kind of a performance graph just given from the lab manual. So here at around like 25 degrees, the blue line is say if we want to achieve negative 20 degrees Celsius, there can only be an additional about say 5 or so watts of heat being added to the cold plate. If it's any higher, then we'll move up in temperature. So like if we're adding 20 watts to the cold plate, that gets us to room temperature, which will be important in a moment. So that's the cooling part. What about the heating? Okay, so we have a resistor, and it's, I mean, it's not just any resistor. It has a large surface area, so it can dissipate the heat to the sample. And it's, ours in particular is 18.5 ohms. We want, so like I said, so we have constant cooling, and then we're gonna have variable heating by just adjusting the power output to this resistor. And we have like you know, an off-the-shelf temperature controller to do that. The controller, it's like a standard feedback controller. So it will read in the temperature through a resistance temperature detector, which is just a resistor whose resistance varies with temperature. It'll take a reading of that. It'll determine the temperature, and then it can either increase or decrease the output to the heater in just like a closed loop, you know, standard PID controller. And it'll have PID parameters that we can then tune. Now, so the resistance in the kind of range of normal temperatures, it varies linearly with the temperature. And so there's an equation that describes this, but basically, if we know the resistance, we can convert it to a temperature. So like, well, about room temperature-ish is about 1100 ohms. Okay, so one of the big things I did was test the cooler performance. Most basic thing is to try to figure out how cold we can get this thing. And so very first thing I did was, okay, we have the temperature controller. I, you know, stuck the RTD onto it. I turned it on and then just measured it over various time intervals. So, you know, like, you know, just after turning on 1, 2, 3 minutes until it reached a steady state where the resistance didn't seem to be getting any lower. That was not very effective because the value I got actually within uncertainty was room temperature, or no, 0 degrees. So it did not actually cool things very much. But then what we realized is that it wasn't really achieving the resistor wasn't achieving proper thermal contact with the Peltier cooler. And so we applied some thermal paste to it and then stuck it into one of the holes in the cooler. And so that essentially meant that the coldness of the cooler was accurately being transferred to the resistor. And so then we got it down to about like negative 20. And so that was good. So in here, okay, I'll get to this. There's another thing though, that obviously when it's just like in the atmosphere, like when your cooler is just in the atmosphere, it is losing heat to the atmosphere. And so I built a little insulation box out of styrofoam to enclose the cooler and, you know, ensured like the heat wasn't exchanged with the environment as best as possible. And so those things combined got us down to negative 20 degrees or so, which, you know, is quite good. We can do a decent range of physics with that. One thing to note though, and this is kind of what all of these charts show, they're just showing how the resistance decreased as a function of time in like the different settings with thermal contact, without thermal contact, which is yellow, with and without insulation, so on, just normalized to the lowest resistance they got, so I could do normal exponential fits. But you can see here that the time constant works out to about like 6.75 minutes for each of these, roughly speaking, which is quite a long lead time for the temperature to change. And I know it's just something to consider for the future. I also tested the heater performance. So for reasons that I'll get to, I couldn't test the full closed control loop system. And so I just did an open loop control where, you know, you connect the heater to the temperature controller and you tell it to output a constant amount of power. Just by the design parameters of our controller, it can only output 18.5 watts to our 18.5 ohm resistor. And specifically in my tests, once it got to about 50% of that value, it began burning the container that I built. So couldn't really test at too high values, but what I found is that at just a couple of watts, it basically doesn't achieve any heating when the cooler is on. Even at 50%, over 50 minutes, it increased by about like 30 ohms. But when you look at that compared to room temperature, it is still significantly below that. So really, we want to control the whole range from as cold as the cooler can get without any heating up till, or not room temperature. This should say no, that is room temperature. Yeah, we want the whole to control the whole range from as cold as the cooler can get to room temperature. And I mean, in theory, you saw per the characteristic graph that if we can output 20 watts, we can get it to that threshold. So once we have a better container, we can test it with that. Now, so what are some of the goals going forward? Well, we want to do closed loop control. The problem why I couldn't do that yet is because the RTD needs to connect to the controller via a DIN connector, which we need to fabricate a cable for. So hopefully I can do that at some point. And then from there, we'll like tune the control parameters and test it in the X-ray chamber that I'll get to in a second. We also might want to improve the cooling capacity, which again can be done by removing more heat from the hot reservoir. And I've looked into getting bigger fans just that like have faster, more powerful rotations for that. Okay, so that's the first part. We can now talk about the copper spectra analysis. So what I did was essentially analyze characteristic X-rays of copper and copper silver alloys. And so characteristic X-rays, essentially what happens is when higher energy particles like photons bombard a crystal, they excite electrons from their like tightly bound states near the nucleus up to excited states. And then obviously those electrons will decay down, and that emits X-rays that we can detect. So there are many different lines that we can talk about. The ones I was interested in here were the K alpha and K beta. So the K alpha is just from the n equals 2 energy level down to the first energy level, and the K beta is from n equals 3 down to n equals 1. And so like these are very well measured transitions for pure elements. So for example, for the copper K alpha, it's about 8,046 electron volts, and for the K beta, it's 8,904. There are actually multiple peaks for both, or like multiple transitions for both because of degeneracy in the energy levels. That's not too important. But so that's for copper. A cool thing we can study is how does this change for copper and alloys? How is it different? And so specifically, we're doing copper and silver. So how are we doing this? Well, we have an X-ray spectroscopy machine. Specifically, we're doing X-ray emission spectroscopy. So the electrons get excited, they get de-excited, and they emit X-rays. So here we have, in this machine, we have our X-ray source, which is just generating a bunch of like non-coherent X-rays. Here, this little thing is where you place the sample. So on this thing, there's a little piece of tape with a tiny like square sample attached to it. And so the X-rays will come here, bombard it, and the idea is that the emitted X-rays bounce off, go through this chamber, and then get detected by this detector. Some practical considerations here are that we don't want other X-rays bouncing off, so we coat this whole, we like shield this whole thing with this little lead box here. And yeah, now what's interesting, so this specific detector type is a silicon detector. For a specific silicon crystal, we also have germanium detectors. This is just the one we always use for the K lines. So that's good. We can now might be able to see here, but this detector can actually like move along this axis, and so we can tune its angle, which is what's known as its theta offset. So when we first inserted the sample into the machine, well, there are a couple things we can tune. We can tune how far away this is from the X-ray source, and we can tune the angle of that. And basically, we just wanted to find the highest peaks. So we ran scans of both of those things, and we found a theta offset of like 0.28 was what maximized it, generally speaking. And then we essentially made the sample as close as possible. So that generally got us good peaks. And so with the experimental plan, we had samples of pure copper, and then we have copper silver alloys of 0.1 copper, 0.03, 0.02, 0.01. So it's getting pretty dilute at the end. And we want to run K alpha and K beta scans on both. And of course, we don't want just like one scan. We want to run a lot of them to get good data. So each scan is comprised of energy ranges that we can set, or just take like what the default energy ranges would be for a K alpha or K beta. And then they're comprised of an energy range and then energy steps. So like how granular do we want our changes in energy to be, and how long do we want to spend on each energy step, and because we're collecting counts data of like how many emitted X-rays do we count. And so that's one scan, and then we want to just run multiple scans for each of these things with the same parameters so we get good data. Now, for the pure copper, this was like excellent. We got just fine data. For the alloys, generally the K alphas were really good, as you'll see. The K betas less so, just because I mean K beta is always it just tends to be a weaker signal, and so we got less of it. Now this you can see is one of the copper alloy samples under a microscope. You can see it's a very like rough surface. You know, it's mostly silver. It should be pretty shiny. And so one of the things we did was like polish the samples with hydrochloric acid to make them nice and smooth. This is not all too effective, but you know, it got a little bit of a better signal. So I'll just show you some of the energy spectra, as well as like the fits I applied to them. So this is the K beta for pure copper. So you can notice a peak around 200, a bit over 225. I just fit it to a basic Gaussian here. It's I mean, you know, it's not a perfect fit. It's a bit asymmetric, but it, you know, it works quite well. It's a clean signal. We've averaged it out, so you can see like the uncertainty is just counting uncertainty, and it's quite low. We also have the K alpha, which here we have two noticeable peaks, unlike with the K beta. And here I fit to a double Gaussian because it very much is like just a bimodal bell curve distribution. Yeah, and so this is for the pure copper. Currently outside the scope of this talk, but like the analysis we want to do on all of these things is just we're going to fit them to Gaussians, and that'll allow us to estimate, for example, the peak amplitudes, the energy at the peak, which should be the transition energy, and then also just kind of the width, the full width at half maximum. The Gaussian provides us all those parameters. And so interesting things to note. So yeah, the K alpha is also significantly higher. Like this is up in 4,000 right now. Now, another sample I'm going to show is for the 0.03 copper in silver alloy. And so here you can see the K alpha. So of course, like much less of a peak, but it's still like, you know, it's still two clean peaks. It still fits nicely to them. I don't want to, so, and you can see the energies, like the peak energies are quite similar here. It's like it was about 80-30 before, still 80-30, and a bit over 80-50 before, still 80-50. The story is a bit less different for the K beta. So the next K beta we got was here, and it is incredibly noisy. As you can see here, this is averaged over 100 scans, so significantly more than the 20 or 30 we ran in the other cases. And it's much less clear of a peak, and it's much noisier signal overall. Of course, here we have what, like 80, around 80 as our peak, and you know, our fit is not all that great, but you know, it's still like the best estimate we can get at the moment. And then yeah, so we have both of these for pure copper 0.03. At 0.02, the K beta just gets to be completely noise and is kind of useless, so we're not really running analysis of that. And yeah, that's basically the idea. I mean, I would have some like concluding thoughts and stuff, but that's currently pending a little bit of work. So yeah, this is where we end off. Thank you so much. Like, you mean for the first part? Well, I mean, so the cooling, the pure cooling is not really a control system. It's just we apply like a direct, like just a constant amount of power and gets a constant amount of cold. For the heating, I mean, the heating seems to work quite well. The only thing we need to do is to increase, like, have a less flammable insulation, and then we can provide the full 18.5 watts to the copper, to the resistor, and that'll get us a very nice range of temperatures. We can also, I mean, that resistor is one of a family of parts, so we can get a resistor that has just a higher resistance value, and that'll allow for more joule heating. For the actual control system, I haven't quite I mean, I haven't gotten to do the proper temperature controlling part yet, but when we do that, and we're gonna have the RTD right in the middle, like where the sample would be. It'll be checking the temperature, and then it'll essentially be telling the controller whether to increase or decrease. Now, I mean, control systems are a subtle art, so there's various like parameters to make it like more responsive and to make it actually achieve the temperatures you want. So there's like auto tuning that we'll do, and then there's also like manual tuning of just like the parameters you can do. So it'll be a bit of playing around with it, but on the whole, I don't think we need like too precise temperature controls. Like within 1 or 2 degrees should be good. Well, the efficiency is somewhat limited just by the nature of the Peltier cooler. We could put it in. So I mean, this it's still like in our okay. So we have an insulating box, and this is currently several pieces of styrofoam that are glued together, which is not the most insulating thing in the world. So creating a better, more serious insulation would just like help with would help with the cooling process, and then also when we're running it, it's going to be in some noble gas like argon or helium or something. And so again, that'll just like help not dissipate heat. As for like actually making it appreciably faster, I'm not sure that is something we can achieve with this design. Like just with the Peltier cooler we have, they'll probably require a different one. But on a more practical note, like when it's running, it's going to be cold. Like on the 6.75 minutes, that is starting at room temperature and getting to as cold as it gets. When it's running, it'll probably already be below zero. And so we can make like, we can tell it, if it's a -15, we can tell it maybe go up to -10. And that should proceed significantly quicker because it very much is like an exponential decay. The initial changes happen fast. It gets down to below zero relatively quickly, but then it takes a while to get to its final value. Not flammable, not actually flammable. It was just but like it would burn without flames. It would just like, get like a little porous here and there. Uh, that's a good question. Something that I imagine there are a lot of like different plastics you could try. Probably something. I mean, something 3D printed might be interesting to try. Um, but honestly, anything like we know how much power we could be putting into the system, and so anything that can, and I mean, we know how much heat that power will deliver. It's just the Joule heating equation. So anything that can survive that amount of heat, I'm sure there are various like plastics that we can we can mold to this box shape that will do the job. I, are we on like we need to. All right. Thanks. I hope that was not too terrible.
Wait, how much are you getting paid for this? Wait. Let me get this straight. If you get an A, you have to pay for $5. So where's the motivation in getting an A if you're gonna lose money anyway? Lol. Hey, my first year was filled with B's. I understand. Yeah. Okay, so you're the next presenter, Ji Zhang. If anyone else is, yeah, yeah, we have him. That's okay then. Hurry up, I guess. Okay. No, no. But once again, like we're going to same constraints as the actual uh, what? Oh, okay. Well, anyway, yeah, good. Yeah. So go ahead. Oh wait, I forgot to give you this.
Okay, let's continue. So you will be also some deficiency in the standard model. And beyond standard model theory, we pack a query mechanism to address it. And also we're gonna go to dark matter part. So why is it important though? In our universe, the matter we can see is only 5%. There are 27%, like 5 times more than the ordinary matter we can see. So addressing that is a major problem in the particle physics area. So we start with the standard model. The world is made of atoms, and neutron, proton made of atoms, and like electrons. But what else? Well, there are quarks and other leptons, like big brother of electron, muons, and tau. Well, we also have 3 forces: electromagnetic force, strong force, and weak force. They all can be described, well, most of them can be described by the standard model, which is a great theory of bringing. We also have the Higgs mechanism to explain the mass of particles. That one is very promising, and physicists love symmetry. So we have different symmetries in the standard model. It could formulate a standard model by 3 types of symmetry group, which is the SO3 for strong force, SO2 for weak force, and U1 for EM force. Why is that? Because symmetry corresponds to conserved quantity, and it's elegant. For example, the U1 symmetry is the local phase symmetry. That one gives electric charge conservation. But broken symmetries will imply massive particles. That is the Higgs mechanism in the standard model. For example, the Z boson acquires mass from this spontaneous symmetry grid. So we have parity symmetry, which is mirror symmetry of this potential. But as temperature decreases, the potential began to change. The blue ball is where the vacuum state is. Right now, we have a non-zero vacuum state. That means the field is everywhere. The symmetry is broken. Then the boson will be this one, the crash method. Well, the standard model is so promising, but it still have some unaddressed problems. For example, in Lagrangian of strong force, we have a term called theta QCD that measures the charge parity variation. Well, but we don't observe charge parity variation in strong force yet. That's because it's related to a neutron electric dipole moment, which is strongly constrained by experiment. So we have a classical picture of neutron. Well, we can like pointing electric dipole moment, but well, that's classical. We have quantum mechanics. That one is very strictly confined. But if someone could find it, the method of finding the electric dipole moment is through precession. So if we put this inside an electric field, it will precess. But we didn't measure that. That one was strongly constrained. That will give in return, a very small upper bound of that CP phase. Well, what could that be wrong? Why is it so small? Someone may ask. And it's not enough for us to assume that is zero. Why the CP is simply to conserve while no symmetries in standard model indicate so? Well, if no symmetry in the standard model, then we promote a symmetry in the beyond standard model theory, which is the Pekier-Quinn mechanism. We promote that one to be conserved to a new U1 symmetry, and then we break that symmetry to have that one to have a little bit of violation. That is constrained by 10 to the minus 11, which you just saw. And that one will give a particle because broken symmetry implies massive particle around mass 10 to the minus 5 to 10 to the minus 2 eV. That's called axion. And based on the property, axion is a very good candidate for dark matter. And here is a picture of axion detection experiment conducted in the University of Washington. Well, speaking of dark matter property, so we go to the real thing. And the definition for it is quite ambiguous because, well, originally it is some observed gravitational effect that does not align with our current theory because we don't see them. They don't interact EM, they don't interact electromagnetism, they don't interact with strong force, they don't interact with weak force. At least that's what we know now. They only interact with gravitational force. So why is it so important? Because we introduce we introduce a lambda CDM model. That model is very important in the Big Bang theory, in the mathematics of Big Bang theory. It basically predicts the formation of large structures, the accelerating expansion of the universe, the abundance of hydrogen, based on many cosmological parameters we observe. But in that model, it requires dark matter intrinsically to explain those phenomena. And here we also have the same image. Well, speaking of the observed evidence for dark matter, so that's the only proof for, that's one of the only proof for dark matter existence. Let's see an example. So for the galaxy, for a spiral galaxy, we could estimate the mass of luminous matter by just either measuring the abundance of hydrogen or just see the start, the abundance of star to estimate the mass. Then we have a very simple formula of rotation speed. So rotation velocity at distance r to the center is equal to this formula, where g is a constant, Newton constant. And mr is a function that takes r to the mass, the total mass within the sphere of radius r. So if we go to large R, we will expect the mr to be a constant because the mass contained is a constant. The luminous mass contained is a constant when we go, like, for example, here. So we should anticipate a decreasing gravitational curve, but no, that's not what we observe. That's in our theory, that's the observation. The rotation is so fast that the curve is flat. That will indicate more non-luminous mass, even extending beyond the galaxy. That's a direct proof for dark matter. So we look at a very specific example. This is the galaxy. The total rotation curve is the fitness graph, the fitness rotation curve. We also have some theoretical prediction of different components contributing to it, like the luminous disk and luminous gas. You can see those two contribute like only a half to the rotation curve. The halo is required, the dark matter halo is required to explain this observed rotation curve. And by this graph, the dark matter inside this galaxy is many times more massive than the luminous matter. Well, that's happening in our galaxy too. In a Milky Way, the total amount of dark matter is 3 to 10 times more than the luminous matter. Well, more massive. That's that's galactic. Let's see the intergalactic observational evidence, which is gravitational lensing, which is by gravitational lensing. So by general relativity, we can see lensing effect. There are two types of lensing used in detection of dark matter. One is strong lensing, another one is weak lensing. Strong lensing, the mechanism is here. Suppose it's very massive black hole here, then it will bend light in different directions. We can see two images from the same thing because the light are bended. But for weak lensing, it's not, the gravitational effect is not so strong to create multiple images of the same thing. But the gravitational field can distort things in a consistent, coherent way, such that we can use those distorted images to reconstruct how much mass is for this yellow blob, which could be dark matter. And that's a very famous example of bullet clusters. So it's collision between two galaxy clusters. One is go this way, another is go that way. Then they collide with each other and passing through. So what this graph tells us, the color map is the X-ray emission. Because when cluster forms, cluster getting to each other closely, the pressure increases, the gas, the velocity of like hydrogen atom increases. So there are brimstone radiation. They create X-rays we can measure. So that's the density of luminance. Another green contour gives the information of total mass, because that's from the weak lensing. Weak lensing only care about mass. So that's the density of total mass. The distinct separation between the brightest area and the peak of the contour is a direct proof for dark matter. And also dark matter could be here. It's pulling apart those two clusters. After looking the intergalactic evidence, we have the cosmological evidence, which is cosmic microwave spectrum. So that's a radiation, photon radiation, early universe that could contain the information about dark matter density. And that could be used in mathematical way of analyzed into spherical harmonic decomposition. What this would tell us is that for this graph, we have multiple normal. That is the basically the numbering for different harmonic modes. And the vertical axis is the temperature. Well, you can see as a power, the power spectrum. This is this graph referred to. The different modes, the signature, the feature of this graph tell us that the second peak indicates there are substantial dark matter. The third peak indicates the density of the dark matter, which is from this graph 5 times more than the abundance of the luminance matter. That's how the first graph, the pie graph you see is from. So that way we could estimate the total dark matter density, total dark matter amount in the universe. Well, those are observational evidence. So beyond standard model theory, we don't have any candidate in the standard model that could be a candidate for dark matter. So we look at beyond standard model theory. We just mentioned before that from the strong CB problem, we proposed someone proposed a Peckier query mechanism that predict the existence of this thing called axion. The axion is light and interact weakly. That's one of the features of dark matter. And in early universe, they are produced not thermally, but by the symmetry breaking of the field. So they are stable and they are cold. Cold just means they are non-relativistic. And they could be abundant now because the field is everywhere in the early universe. So that makes it a very good candidate for that. And here, this is the experiment, experiment, the theory of that experiment conducted in the University of Washington that you just see before. So we, inside the chamber, we apply very strong magnetic field, EM field, and that's allows, that could create, increase the probability of axion interacting with those virtual photons and becoming a real photon, which we can detect. And another possible candidate of the dark matter is WIMPs, weakly interacting massive particles. That one is, instead of axion, which is product non-thermally, they interact thermally in the early universe. That means they interact with standard model particles. And at the time when the universe cooled down, they froze out and fixing its abundance. Thus, they are cold. They are non-relativistic because they froze out. And based on this statement and some calculations, we could estimate its mass range from 100 GeV to 1,000 GeV. Coincident, what a coincidence. In supersymmetric theory, they predict lattice neutrinos, which is the partner of the neutrino in standard model. They are also considered a potential candidate for the WIMPs. That's actually called the WIMPs miracle. So two independent series predict the same thing. So people are searching for the WIMPs. So that's a typical WIMP searching experiment. We have the WIMPs wind from the galactic halo. They could hit the target nuclei in the laboratory and create elastic collision. And the recoil energy, the recoil momentum of the target nucleus can be measured. Thus to predict, thus to measure the WIMP's mass and its velocity. Yeah, that's all of my presentations. We start with the standard model, and we go to a deficiency standard model, which is one of the examples called strong CP problem. The Pecky-Queen mechanism promote that CP violation phase to a new symmetry to address that problem. And dark matter, which is a huge problem in the standard model, we mentioned a few of its observational evidence, which is this one is inside the galaxy, and this one is intergalactic, and that one is cosmological. And no candidate in the standard model has correct property to be a dark matter. So we look at beyond standard model candidate for the dark matter, which are WIMPs and axion. They have distinct properties. And that's all for my presentation. Thank you. So the cosmic wave background will give us the information about how much there, what is the density of dark matter in the early universe. And we actually use the information, the density of dark matter, to calculate the mass range for WIMPs. So yes, it's related. The abundance here, fixing its abundance. The abundance here is just referring to the current density of dark matter, which we observed from the cosmic wave background. 15. How do I carry this kind of experiment? So if if this kind of particle is like how the theory described, then it's attracted by the gravity. So in our galaxy, it will be the supermassive black hole in the center of the galaxy. So the rotation speed of our planet with respect to the center of the Milky Way is exactly, well, it's roughly this number. So that's why the velocity is assumed to be this number. And when it hits a nucleus, well, it could hit either electrons or nuclei. When it hits those two stuff, it will create recoil energy, which recoil energy can be measured because that's a standard model stuff. We have very good understanding of standard model stuff. For example, suppose we have a detector medium made of germanium and silicon. When a particle hit that, when a dark matter candidate, well, when a WIMP's particle hit that, it will create vibrations. The vibration, because it's a rigid body. It's not a perfect rigid body, but it's a rigid body. It creates vibration, which could be picked up by the, let's say we've placed some TEC here. What's the name for that? Well, the TEC device. And the TEC device have some, and also we put some thing together, which is super close to each other, but not touching each other. But when a vibration happening, they will touch each other. Then that gives the information about what is the energy for this kind of vibration. And that gives us what is the initial collision energy, what is the mass of WIMPs. So all the experiments try to do, the first thing is to determine the mass of WIMPs. So that's actually review the fact that we know nothing about dark matter. We don't even know its mass, the particle constituted to it. Yeah. What? Did I give that to you?
In a presentation. Yeah. You know, I actually I didn't do mine with Eka, but last year I did a dark matter one with Blood Diamond. Oh. Yeah. And so I actually, you know, for example, that specific one I also used in my presentation.